Assalamualaikum warahmatullahi wabarakatuh. A very good day. So for chapter number 5, we will discuss about biodiesel fuel effect on fuel deposition. Introduction about unburned fuel impingement. So the figure shows the bottom view of a combustion chamber. So we have combustion chamber wall. So normally for diesel engine, the temperature of the chamber walls is within 127 degrees Celsius up to 450 degrees Celsius. And we have at the middle we have injector with 8 holes. We have fuel spray, and the area within the I call the red circle is the impingement area, where this area refer as the area that will have high possibility for deposit formation. And for this case, we will have, due to in terms of number of spray, we have 8 sprays, so we will have 8 area that will have high possibility for deposit formation in the diesel engine. So so there are a few phenomena that involve with fuel impingement, fuel spray impingement in the engine. So the schematic diagram shows the schematic diagram of the fuel spray that impinge on the hot wall. So hot wall normally we refer as the wall of combustion chamber or the surface of the piston. Okay, so normally the spray will consist of thousands of small droplets, and so we need to know to study what I call the effect of spray impingement, and also the droplet impingement on the hot wall surface. So for fuel spray impingement on combustion chamber wall, there are two cases. So first case is the condition after the combustion process, where there will be the impingement of unburned fuel on the chamber wall. And the second case is before combustion, and for this condition we will have fresh fuel impingement because the combustion still not start yet during the before combustion condition. So these cases we need to consider when we discuss about fuel deposition in an engine. Unburned fuel impingement mechanism in an engine. So in the figure shows the the injector tips, spray holes, combustion chamber wall, or or in our explanation sometimes we refer as the hot wall. So from the spray holes, the injector tips will produce the fuel spray that impinge on the combustion chamber wall. So the process will involve with thousands of fuel droplets, where at the beginning fuel will mix with oxygen, enter the combustion chamber. During that time, the temperature is around 60 degrees Celsius. Okay, so the yellow color circle represent the unburned fuel. And then after the temperature increase inside the combustion chamber, when the temperature increase up to 140 degrees Celsius up to 250 degrees Celsius, the fuel is superheated and expand. So you can see that the diameter of the droplet increase due to the expansion process of the fuel. Then after a specific pressure, high pressure and also high temperature, and the temperature normally for diesel fuel is around 400 degrees Celsius up to 600 degrees Celsius. So the combustion, the droplet will combust or detonate. However, part of the droplet still not combust, and this droplet that not go through the process of combustion will refer as unburned fuel. And then after the combustion complete, um, after the combustion process complete, so the combustion will produce exhaust gas at temperature of 600 degree up to 1000 degree. And from the combustion process, the process will produce particulate matter, NOx, and also uh, the called the unburned fuel as shown in the figure. Okay, so the unburned fuel that impinge on the wall will form liquid fuel films, and this will cause the deposit formation on the chamber wall as shown in the figures. So this is how the unburned fuel that impinge on the wall contribute to the deposit formation in an engine. Fuel deposit mechanism. So when in an engine, fuel impingement occur in an engine on the chamber wall. So actually, the process will involve the impingement of thousands of droplets, fuel droplets, on the chamber wall. So we will have droplet wall interaction. So we need to know what kind of droplet to wall interaction. So there are numbers of behavior that occur due to the droplet impingement on the hot surface. So for example, in the figure shows when the what I call when the temperature of the wall within the nucleate boiling regime. So we have what I call the formation of your film on the hot wall, and for the transition boiling regime, so we'll have different type of behavior such as splashing of droplet and also bouncing of droplet. So we will learn detail about the droplet behavior on the hot surface later on. And this behavior of the droplet wall interaction will determine the amount of deposit formation on the hot wall. So as we know, as we learned before about the deposit mechanism that suggested by Lepperhoff. So we have a few processes involved in deposit formation. First, we have the condensation of gases component where during the process the thin film of fuel will form on the wall, and then the process of impaction of particle on the thin film. So this process involves induction phase, and then the third process involves absorption of gases component into the what I call absorbed by the deposit material that already attached on the wall. And the final one, due to the compression of the layer and also the action of the hydrocarbon, so the black carbon deposit will finally form on the combustion chamber wall. So these are the processes involved in deposit formation in an engine. Okay. Fuel deposit investigation. There are three types of fuel deposit investigation. First, we have actual engine test, where the first figure shows the schematic diagram of the actual engine, and the second photo shows the actual engine test in order to investigate the fuel deposit that form in the engine. So in this investigation, the investigation will collect or measure the amount of deposit accumulated in actual engine. Then the second investigation is about the fundamental investigation. First, we have spray test spray investigation or spray test. So we have in this test, we will investigate about the fuel spray behavior for different type of fuel, and also we can test about the deposit formation due to fuel spray impingement. Okay, so this photo, the second photo under the spray test category, shows the actual apparatus that used to check or investigate this fuel spray behavior and also fuel spray deposition. And the third type of investigation is about the droplet test investigation. And the function of this test actually to investigate the fuel droplet evaporation characteristic, and also to investigate the few droplet deposition. Okay, so the last photo shows the actual what I call the experimental apparatus for few droplet deposition tests. Okay, so this is three type of few deposit investigation. So we have actual agent test, spray test, and also droplet test. Okay, first we look at the few droplet tests. So droplet test apparatus, as shown in the schematic diagram, consists of what I call fuel tank to store the tested fuel. So we have control valve used to control the dripping interval of the droplet impinged on the hot surface plate. We have thermocouple to control the temperature of the hot surface plate, and also the heater control panel coupled with the thermocouple in order to control the temperature of the hot plate. High-speed camera was used in order to observe the behavior of the droplet during the evaporation and also during the deposition. Okay, so this is the simple test apparatus for the fuel droplet test. So in terms of parameter during the investigation, first we have type of fuel, different type of fuel. Second, different tips to surface distance. And the third one is the plate temperature. Okay, so from this investigation, the main data that we will obtain is the evaporation characteristic of fuel. So the graph shows the general features of evaporation characteristic for diesel fuel. So in terms of information that we have from this characteristic is the droplet lifetime versus surface temperature. Okay, so if droplet lifetime increase, that's mean the evaporation rate of the fuel will reduce. Okay, so in this graph we have a curve that represent the evaporation characteristic. So we have few important point here. First we have MEP, point that refer to maximum evaporation rate point temperature, where at this temperature the fuel droplet will have shortest time during the evaporation, which means the evaporation rate for the droplet at this temperature will be highest. And the second point is the Leidenfrost point, the point where what I call the the evaporation after MEP, the evaporation rate the droplet lifetime increase, and at certain point where the what I call the droplet lifetime start to decrease again, we refer as the Leidenfrost point. And normally the Leidenfrost point happen at very high temperature, around 600 degrees Celsius. So the droplet lifetime will describe or represent the evaporation rate or evaporation of fuel droplet. Okay, so from the experiment also we can observe the droplet surface interaction behavior when the droplet impinge on the hot surface. So for example, at low temperature as shown in the point in the graph, so we'll have when the droplet impinge on the hot surface, so we'll have lens shaped droplet where the droplet will attach on the hot surface and vaporize. However, when the temperature close to MEP point, so we'll have numbers of behavior. One of the behavior is we will have vigorous boiling. So the droplets still attached on the surface, but in terms of evaporation rate will be high at this point. Sometimes due to the depend on the tips to surface distance, so we will have broken film on this hot surface, or sometimes we will have a single droplet attached on the hot surface, but we will have splashing of very tiny droplet. Okay, so these are few behavior that we'll observe when the temperature of the surface temperature very close to MAP point. So after MAP point, so before MAP point, actually when we increase the surface temperature, the droplet lifetime will increase, which means evaporation rate, droplet lifetime will decrease, which means the evaporation rate of the few droplet will increase when the temperature increase close to MAP. But however, after MAP point, the droplet lifetime will increase again, which means the evaporation rate after MAP will reduce. In terms of behavior after MAP, so we will have special behavior where the droplet, so we'll have single spherical droplet that bouncing on the hot surface due to the formation of vapor layer under the droplet. However, due to the maybe high tip to surface distance, we also will have this kind of behavior where we have breakup droplet, but still the droplets still bouncing on the hot surface. And also we will have what calls spherical droplet behavior at Leiden frost point with higher value of droplet lifetime. So we need to know this behavior in order to understand the few droplet deformation. So this behavior is one of the factor that can be used to explain the few deposit formation in an engine. Now we'll discuss about the evaporation test result in terms of droplet surface behavior. So in terms of droplet test condition, so the fuel tested are diesel fuel, B5, B10, B20, and also B100. Tip to surface distance, so we have the result for 60 mm, 148 mm, for surface temperature difference of 250, 357, 450, and also 600 degrees Celsius. So the temperature of 357, actually this temperature is some sort like the reference temperature of MAP, where this temperature is the MAP for the typical diesel fuel. Okay, so that's why we have some sort like called very obvious data if you compare to the other surface temperature. So we have specific data of temperature at 357 degrees Celsius. So this is what I call the result in terms of droplet surface behavior when the surface tip to surface distance at 60 mm. So this photo actually captured by using high speed camera. So at 250 degrees Celsius, we can see that all fuel tested will have same the droplet surface behavior when the droplet impinge on the surface of the hot wall, where we have lens-shaped droplet where the droplet attach on the hot surface and then vaporize. So at this point, normally the droplet lifetime is very high, so we will have low rate of evaporation. After we increase the temperature of the hot surface at 357 degrees Celsius, where this temperature actually is the MAP point for the diesel fuel. However, for the other type of fuel, this temperature actually very close to their MAP temperature. Sometimes the MAP temperature will have quite similar with the MAP temperature for diesel fuel. So if you look at the behavior, so we'll have three types of behavior A, B, and C, depend on the type of fuel that we use. So for BDF, B5, and B10, we will have in terms of behavior, so we will have vigorous boiling behavior where the droplet still attached on the hot surface, but the evaporation rate will will have very high evaporation rate. So this is probably due to the MEP point for B5, B10 is similar to the MEP point for DF. Okay. However, for B20, so we will have spherical droplet behavior where the droplet bouncing or rolling on the hot surface due to the formation of vapor layer under the spherical droplet of B20. So one of the reasons why this happened, this is because the MEP point or temperature for B20 is slightly slightly lower than 357. Okay, so that's why we have this kind of spherical droplet. However, for B100, the in terms of behavior still will have the lens-shaped droplet behavior, where this shows that the 357 degrees Celsius actually far lower than the MAP temperature for B100. Okay, next, when we increase the temperature to 450 degrees Celsius, all what I call tested fuel will have the same droplet surface behavior, where different type of fuel will have the same behavior in terms of droplet fuel interaction, where the droplet bouncing on the hot surface. And if you make comparison between the temperature 357 degrees Celsius, so at this time, although the I call the droplet bouncing, so the droplet lifetime will be higher compared to at the condition of 357 degrees Celsius. And further, after you increase the temperature to 600 degrees Celsius, so we'll have similar behavior as same as at surface temperature of 450 degrees Celsius, where the droplet still bouncing. So we have single droplet bouncing on the hot surface. However, depend on the fuel. For example, like B100, sometimes we will have broken droplet behavior. However, the droplet still bouncing on the hot surface. So we will have more than one droplets bouncing on the hot surface, especially for B100. Okay, next, the result obtained for tip to surface distance at 148 millimeter. So we'll increase the tip to surface distance. And so at temperature 250 degrees Celsius, so we have similar behavior, as the result I obtained for tip to surface distance at 60 millimeter. So we have all the tested fuel shows the lens-shaped droplet what I call lens-shaped droplet behavior. So when we increase at 357 degrees Celsius, so when the tip to surface distance at 148 millimeters, so we have quite different behavior for diesel fuel, B5, B10, also B20, where we have, for example, like B20 and also B10, we have the broken film behavior. However, for B5 and DF, we have breakup droplet that bouncing on the hot surface. So we have very small droplets, multiple droplets that bouncing on the surface for DF and also B5. However, for B100, still maintain in terms of behavior, maintain the lens shapes droplet behavior, where the droplet attach on the surface and evaporize. Okay, so when we increase at 140 degrees Celsius, so most all of the tested fuel will have the same behavior, where the droplet break up and bouncing on the surface of the hot wall. So we have multiple droplet bouncing on the surface of the hot wall for all tested fuel. Similar behavior also occur when we increase the temperature to 600 degrees Celsius. So these are the behavior of the different type of fuel when we change the tip to surface distance and also the hot surface temperature. So we will have different what we call droplet surface droplet surface behavior, that this kind of behavior will affect the amount of deposit accumulated in the engine. So we can use this behavior in order to explain what happened inside the engine. Okay, the summary of droplet surface interaction behavior. So we will have this kind of what I call the droplet lifetime evaporation characteristic as example. So as we discussed before, so we have in terms of droplet surface behavior, the F, B5, B10, B20 have similar droplet surface interaction behavior. When impact force increase, the breakup behavior tendency also will increase. So possible condition in actual engine, the high impact force will occur due to the high pressure fuel injection. At high surface temperature, the detached droplet formation tendency will increase. So possible effect in actual engine, hydrocarbon and soot emission tendency will increase. Deposit formation tendency will decrease. As shown in the figure, shows the cross section of the single cylinder engine. So what happened for high surface temperature, when the fuel spray impinge on the hot temperature wall. So let's say the unburned unburned liquid fuel droplet impinge on the wall. So we'll have the detached droplet. The droplet will break up to the detached droplet, and the droplet will not attach on the surface. So this will cause what we call the formation of soot during the combustion due to the high temperature and high pressure. So the possibility the detached droplet will change into soot will be high, and then the soot will release through the exhaust pipe, and part of the droplet of the detached droplet that not change into soot sometime will release through the exhaust pipe, and this droplet we consider as the hydrocarbon emission. So that's why if this condition occur where the droplet detach what we call the droplet detach from the surface of the combustion chamber, so hydrocarbon and also soot emission will increase, and at this condition the deposit formation will decrease. However, at low surface temperature, attached droplet formation tendency increase and deposit formation will increase. So possible effect in the actual engine, the deposit formation tendency will increase if the surface temperature very low. Okay, for example, so when the fuel spray impinge on the low temperature wall, so the unburned liquid fuel droplet will impinge on the wall. And in terms of behavior, so we'll have attached droplet behavior, lens shape behavior, where the droplet attach on the wall and vaporize. However, if the liquid a thin film form and still remain on the wall. So this called attached droplet will change into deposit. So that's why at low surface temperature, the possible effect in actual engine, deposit formation will increase on the combustion chamber wall or on the piston head.